Okay, so we had the X was the total weight of chicken to be purchased, and Y was the cost of chicken in dollars. Remember our criteria for defining variables well? We had 3 criteria. So that should be imprinted in your mind. Don't ever forget that and practice it. Okay, so then we looked at changes in X, right? We looked at some changes in X and corresponding changes in Y as a new variable based on change in X, a new variable based on X, change in Y, a new variable based on Y. Okay, signifying a change. All right, and then we were looking at the graph and we were representing those changes on the graph. Let's see if I can. New graph here. Okay, there's our graph. Smaller, okay. And then we said we could add the line through them, and then we talked about how many points are on that line. How many points are on that line? Just 5, right? No, when you look at a line, a graph, a curve, or a line that's a graph, the way that your image of it, the way you think about it is that it's just many, many points. And each one of those points, in this case, is what? So if I pick this point right here, what does that point mean? Can you articulate exactly what that point means right there? What is it showing? What is it signifying? Tell me, what's your name?
My name is Valerie.
Valerie, what does that point mean?
That point means that there's it's the points at 10 and 20. So whatever the bottom is, it doesn't stand.
It's this one of these.
Oh, okay. So the weight of the chicken is 10, and the total cost would be about 21. I would say.
10?
Oh, sorry. 7.
7. So she said when the weight, that point means that when the weight is 7, the cost is?
About 21.
No, it's actually this right here. So it's not about. Yeah, so we got an exact point here. So when the weight is 7, the cost is 21. That's what that point means. When the weight is 7, the cost is 21. And that line represents a zillion points, just like that. Amount of chicken and the cost. And then we talked about then representing the changes on this graph. So let's look at, say, this one. How can I represent the change of x from 7 to 12? That's a change of x of 5. How can I represent that? Where would I start, first of all? Where would I start if I want to represent the change in x from 7 to 12? From 7 here? I could. Down here I could show that change in x down here in the axis, but we want to actually show it from this point. And which way should I go? Up, down, left, or right? And I'm going to go over how far? Change in x is? That's supposed to be straight. Not the best line of drawing all day. It's getting better. Okay, good. All right, change in x is? 5. Right there, from 7 to 12. So I'm showing the cost, or the pounds increasing 5 pounds starting at 7. And when that happens, how much does the cost change? It goes up by 15, and we can show that with a vertical line because our vertical scale is showing cost. So that we could label that delta y equals 15. Really important. This is definitely something used in calculus all the time. Looking at the change in one quantity and the corresponding change in the other. Okay, how could I represent from 12 to 3? So where would I start here? Top point, and I'd go up, down, left, or right? Left. Now, delta x is negative, so that means we're taking chicken off the scale, or we're reducing the amount of weight. Delta x equals? Negative 9. And the corresponding delta y then? So when we take that many pounds off the scale, our cost goes down by 27. And decreasing quantities have a negative change. Decreasing quantities have a negative change. So this way of showing one change and the corresponding change in the other on a graph is important. Okay, very important. And so then we talk about these numbers here. So we've got 2 and 6, 6 and 18, 5 and 15, negative 9 and negative 27. They have a special relationship. What's the key word? Okay, it has to do with a ratio. We have, starts with P. Proportionality, right? We have proportionality in the changes. When you have proportionality in the changes of two quantities, that's equivalent to saying that you have what? Anybody know?
Constant rate of change.
Right. So let's show this here. Where am I? When the change in y is proportional to the change in x, I should say we have constant rate of change. Okay, so there are three mathematical results of this. So this is kind of the overall definition of constant rate of change, that the change in x is proportional to change in y. But there's three mathematical consequences that we need to know. We need to know them well. This is how we're going to analyze two quantities based on these mathematical principles that are all equivalent to saying we have constant rate of change. First one has to do with proportionality. So when you did proportionality problems, what did you do? You set up. What did you do in proportionality problems back in junior high? Is that x equal to y? No, not quite. What's that?
Table of values.
Table, and then what? Divide, right? Ratios. So what's always the same here? The ratio of what to what?
X to Y.
Not x to y. I mean, yeah, in this case it is, but we're really focusing here on the changes. The change in y to the change in proportionality of two quantities, then those two quantities maintain a constant ratio. And so we have proportionality of the changes. So delta y over delta x is a constant. And what is that constant here? 6 divided by 2. 18 divided by 6. 15 divided by 5. You get 3 in this case. And that's our constant rate of change, $3 per pound. $3 per pound. So that ratio of delta y to delta x stays constant, and that number is the value of the constant rate. All right, what's another consequence of this? Do you see that no matter what delta x you start with, what do you do to get delta y? Multiply by 3. This is called constant multiple. So given any change in x, multiply by 3, it gives you the corresponding change in y. Okay, so delta y is a constant multiple of delta x, or delta y equals k delta x. What is the constant multiple? In this case, it's 3. It's that same number. It's the value of the constant rate of change. Okay, then there's one more mathematical result of constant rate of change, or proportionality in the changes, and that is, so look, if the weight of the chicken changes by 2, how much does the cost go up? How much does the cost go up if their weight changes by 2? And they all said in chorus. If the weight changes by 2, how much does your cost go up? Everybody's. $6, right? $6. That's the change in y. I'm asking about the change in y. What about if the change in 2 pounds was starting at 10 pounds and ending at 12 pounds? How much does your cost go up? Starting at 10 and ending at 12. How much does your cost go up? 6. Starting at 20, ending at 22.
6.
Starting at 1.5, ending at 3.5 pounds. 6. No matter what change of x you have, that's 2, starting anywhere. If you change x by 2, your cost will always go up 6. Agreed? That's the third. And then what about if the pounds goes up by 10, say from 2 to 12? How much will our cost go up? And what if our change goes from 70 pounds to 80 pounds? How much will our cost go up? Still 30. Okay, so this is this third thing, and it says that if you have equal changes in x, the corresponding change in y will stay consistent. If you have equal changes in x applied in different places in your change in quantity, it doesn't matter where you take that change in x, you're going to get the same change in y. That's constant rate of change. Okay, so these are these three very important fundamental mathematical results of saying that the change in y is proportional to the change in x, or we have constant rate of change. So let's summarize those quickly here with got a little PowerPoint slide that helps kind of reinforce this. Any questions on what we're talking about? Okay, so the days of y equals mx plus b are over. We're taking this to a far more profound level. Okay, we want to look at constant rate of change in terms of really investigating what's happening with the changes in quantities. What two quantities are we talking about being in constant rate of change? What two quantities are we talking about being in constant rate of change? Yeah.
The weight of the chicken and the cost of the chicken.
X and Y, okay? So our focus, we're spending all this time over here, but we're really, all our analysis is about these two quantities. What's happening between those two quantities? If you have constant rate of change between, say, X and Y, then the results all have to do with the changes. That's why we're spending so much time over here. But we're talking about, do we have constant rate of change between X and Y? We're not talking about, do we have constant rate of change between delta X and delta Y? We're using those as a vehicle to analyze the relationship between X and Y. Okay? So let's do, where is it? Here. So this is just a summary, and it's pretty. Okay? So two change in quantities vary together at a constant rate if the changes in the quantities are proportional. Here are the three mathematical results. Equal changes in one result in consistent changes of the other. That was our number 3. The change in one is a constant multiple of corresponding change in the other. That was our number 2. And then corresponding changes in two quantities maintain a constant ratio. Delta y over delta x stays constant. That was our number 1. So let's see what that looks like graphically. First one, equal changes in one quantity. So here's showing equal changes in one quantity result in a consistent change in y. Not the same as the delta x, but the same as each other, right? Consistent delta y. So that's one mathematical result of constant rate of change. Okay, constant multiple. That if you want the change in y, how can you get the change in y in any given situation? You can multiply the change in x by our constant multiple, and it will give you the change in y. So this is the idea that delta y equals k delta x, where k is constant. And k is the value of the constant rate of change. Make sense? And finally, what's the last thing that's true? Remember? Jonathan, you remember? What's the last thing that's true? So that was the one that was the first one we did. So what's the one we haven't done yet here on the graph? Okay, that was the one we just finished. That's the other one.
Changing y over changing x is constant.
Right. So the two quantities, the changes in the quantities maintain a constant ratio. So what does delta y over delta x1 equal? What does that equal? Tell me your name right here. Yeah. Yes, you.
Jenna.
Jenna. What does delta y1 over delta x1 equal? K, and how else could we get the value of k?
Using values.
No, if we were just looking at what we've got here on the screen, what's another way we could set up a value that's the same as that ratio of delta y1 over delta x1?
Using the slope of the graph and in the equation y equals x plus 2.
Okay, we're kind of getting off track. Jacob.
Delta y is equal to delta x.
Yeah, so no matter, so corresponding changes maintain a constant ratio of delta y2 over delta x2, also delta y3 over delta x3. So that ratio is a constant. And that constant is the value of the constant rate of change. Of delta y with respect to delta x? No, it's the constant rate of change of y with respect to x. Again, we're focusing on the changes, but the quantities that we're analyzing are y and x. Okay? Questions on that summary? Okay, so let's practice. Let's practice this. New example. Okay, so contents. Read. So you're going to read the green and the blue while I'm getting set up here. So the green is the setup, and the blue is your tasks. So we read the green and the blue. I think we're back to square one here. Yep, I think we got it. So a soldier lowers an American flag from the top of a flagpole that's 14.5 meters tall. That's our scenario, okay? So we're going to spend 20 minutes on this from this one sentence, okay? And so in your homework, you may get one sentence. You're not going to get all this hand holding, okay? I'm going to hold your hand through this whole process. You're going to work on it, but I'm really going to lead you through and guide you on how to approach this. Where the rubber really hits the road is if you can have a situation like this and you can take the initiative to do an analysis like this and apply what we're learning about constant rate of change, okay? Let's turn this off. Arg. What the heck? I'm all over the place. All right, finally, we're back. Okay, so oh, jeez. All right, let's just leave it at that. So number one is done, okay? Number one is done. These are the height and time variables defined. Remember, you're responsible for the 3 criteria of defining variables well. We'll be practicing that all semester, so just ingrain it in your mind and don't forget the 3 principles. But here's well-defined variables. Time elapsed in seconds since the flag began to be lowered. The height of the flag above the ground in meters. Those both meet all 3 criteria. And then to find the corresponding delta t's and delta h, well, delta t is just the change in time elapsed since he started lowering the flag, and the change in height of the flag above the ground in meters. Okay? So you're going to do 2 through 4. Number 2, you're going to find, using these tables over here, you're going to find intervals that result in this value of delta t. And so you're going to find 3 different intervals that give you a delta t of 1.5. And then 2 different intervals that give you a delta t of 3, 2 different intervals that give you a delta t of 5, etc. Okay, that's your number 2. So people may have different responses here. Okay, and then number 3, you're going to find the change in height in each case. You can just use, once you've selected your starting and ending values of t, then you just come over here to the table and use those corresponding values of height to calculate the change in height. Then number 4, what 3 questions can you ask to determine if h varies at a constant rate with respect to t? So now we're practicing what we learned. I'm going to take attendance. Any questions on your 3 tasks, number 2, 3, and 4? Does that make sense? Is it clear? Okay. And sir, why don't you come up and join us? Yeah, don't sit in the back half, but we'll see. We're getting a new classroom, so we'll see what happens next. But go. You can work together. Jerome can help you.
Is my name not on your roster yet?
Yeah, you want to tell me afterwards?
Yeah.
All right, where is Abdullah? Did you get some of these that are going to be we're going to change by 1.5? Tell me what you got. From what to what? 3.5 to?
You said 3.5 to 2.
3.5 to 2? Is that going to make delta t change by 1.5? No, that would be a decrease in the time quantity. Yeah, we have these are positive changes in t. So how can you change that to make it positive? Yeah, so start with 2. Okay? So you get another one?
For 1.5?
For 1.5, yeah.
3.5 to 5.
3.5 to 5.
5.5 to 7.
Oh, your voice changed. Becca wants to do the next one. What did you say, Becca?
5.5 to 7.
5.5 to 7. There are others. There are many others. These are 3 possibilities. Okay? Oh, I'm using that for roll. Okay. And so, Becca, to keep going, what'd you get for the change? So 5.5 to 7, what'd you get for the change in h?
Negative 1.8.
She got negative 1.8. Did you do either of these other 2?
Negative 1.8.
Did you do these?
Yeah.
And you got negative 1.8? Actually. Okay, somebody new. Where's Carlo? Carlo's not here. How about John? Tell me about a delta t of 3. What did you get for starting and ending values of t?
7 to 10.
7 to 10. Did you get another one?
5.5 and 8.5.
How did he do? Did you get it?
Yep.
And John, did you calculate the corresponding delta h for those? Just tell me how you could do that. How you would do that. So if you're going from 7 to 10 in t, what would you do to calculate the change in h? You're going from 7 to 10. What was it? You're going to do 6.1 minus 2.5. What do we think? Is that right?
It would be 2.5 minus 6.1.
She wants 2.5 minus 6.1. So when you do a change in a quantity, you do starting value minus initial or initial minus final? I'm sorry, initial minus final or final minus initial? Heads I win, tails you lose. Okay? So what do you do? Final minus initial. So what will you get? Negative. This is the height is decreasing, right? Yeah, negative 3.6. Right. Okay, how about changes in 5? Dan, you're up. Changes in 5.
So I got 0.0 to 5.0, or 0 to 5.
0 to 5.
Then I got 5 to 10.
5 to 10. Those work? And what did you get for the changes in the height for those changes in time?
I got negative 6.0 for both. Negative 6.
You got negative 6 for both. Agree? Cool. All right. And finally, of the data that I gave you, there's only one possibility here. From 0 to 10. Change in height would be 2.5 minus 14.5. Negative 12. Okay. So you may have slightly different, or you may have different intervals here, but the changes should be the same, and those values should end up being the same as well. So what 3 questions can we ask to see if h varies at a constant rate with respect to t? What is one of the questions we can ask? How about Zach G? What's one question we can ask to see if h varies at a constant rate with respect to t? Not sure?
Is the distance, or is the relationship between time and height linear?
Okay, that's true. That wasn't the 3 that we were focusing on, eh? So that's true, but how do we know if it's linear or not? So mathematically, how do we see if it's linear? Tell me your name here and the white and the glasses. Yeah. Madison. What is one question I can ask to see? Okay, so then what would that be in this situation?
So then this one would be delta H divided by delta T.
She wants, if delta H divided by delta T is a constant, we'll have constant rate of change. What do you think? Okay, cool. What else? Michael.
Delta y is equal to k times delta x.
Okay, but we talked in this case.
Okay. So that would be the delta h equals k times delta t.
Is delta H a constant multiple of delta T? Is delta H equal k delta T? All right, and what's the last one? Bahia. So we got constant ratio of delta H to delta T. We have constant multiple. Delta H is always k times delta T.
If delta T has equal change, consistent equal changes as delta H.
Okay. If you have the equal changes in T, do you get a consistent change in H? If you have equal changes in T, do you get a consistent change in H? Okay, so we got them. Let's write those down here. And then let's answer those questions. The first one I have written is, do equal changes in T result in consistent changes in H? Yes or no? And how do you see that? Every time delta T is 1.5, what happens to delta H? The flag goes down 1.8 meters every time 1.5 seconds goes by. Every time 5 seconds goes by, how far does the flag go down? 6 meters. It changes, the quantity H changes negative, the change in H is negative 6. So we can't test every possible value, but with all the data we have, it sure seems like, yes, equal changes in T result in consistent changes in H. Okay, how about, does the change in H and the change in T maintain a constant ratio? How would we check that? Is it Nathan? How would we check that? So we're going to check to see if change in H and change in T maintain a constant ratio. What would we do?
Divide the change in height by change in time.
Just pick one of them?
Yeah.
And then we're done?
You divide it by the change in time.
Okay. All right, so I'll do that here. That's there. I need more space to this. There we go. So there's that ratio. Okay, anyway, you can see it over there, negative 1.2. So does that confirm it right there? Does that confirm that we have constant rate of change? By just doing negative 3.6 divided by 3?
No.
No. What else would it have to do?
Oh no.
Okay, is this Rebecca over here, the hat? So he wanted to take delta H over delta T, and we got negative 1.2, and we're asking, does the change in H and the change in T maintain a constant ratio?
Let's do that for a couple ones and make sure we're on the same.
Okay, so we're going to do it for more rows. All right, so I'll take that, I'll copy that. So actually that's based on dividing these two, so I'm just going to copy that to all of them. So now I did it for all of them. I divided change in H divided by change in T. What do we see? State of constant, right? State of constant. Looks good. What about the ratio of the value of H to T? So I want you to calculate, for this at 3.5 seconds, I want you to find the ratio of H to T, and then again at 8.5 seconds, find the ratio of H to T. Go. So find the ratio of H to T at 3.5 seconds and at 8.5 seconds. And find those numbers. Did you get it? I got 2.943 for the ratio of H to T when T is 3.5, and 0.506 when H to T is when T is 8.5. So my question is, are the quantities for T and H, those variables, are they in a constant rate of change relationship? Yes or no? I heard two no's. Everyone's going to say no? Say yes. Okay, why don't you talk about it with the person next to you? We just got that H over T is not in a constant ratio. It's changing. Question is, are H and T in a constant rate of change relationship? Talk to the person next to you. Go.
T and H. The rates. So even though the ratios however, H and T are not in the ratio.
You're the one that's delta H instead of
It's the rate. It's the ratio of T and H.
they want H to T.
Okay, Sean Longe. What do you think? Yes or no?
I'm still saying no.
Still say no. Why?
Just it doesn't, that last criteria doesn't follow it as if I was going off of the here.
So you're saying T and H are not in constant rate of change.
Yes.
Why not? Why are they not in constant rate of change? Okay. All right. This is Andrew? Nick, sorry.
I'm going to say they are in constant rate of change.
He says yes.
Because delta H over delta T across all those different points is negative 1.2.
Okay.
So it's the same ratio of change.
He's saying the changes are in the same ratio. Therefore, H and T are in constant rate of change. Michael, what do you think?
According to the criteria you gave us, you said we're looking at the delta y and delta x, or whatever values it is, which would be delta t and delta h in this scenario. So looking at the deltas, and those are in constant rate of change, which means that we do have that, so it should also be applied to that, I think.
Okay, so this is good. I'm glad we're talking about this. Does this constant ratio of delta h to delta t, does that mean that delta h and delta t are in constant rate of change? Or is that what we're looking at? That's not really the question we're asking. So our focus is, are h and t in constant rate of change? And the criteria to check that are the ratio of the changes. This is okay. This doesn't phase us. Yes, time is increasing and the height is decreasing. So this ratio of height to time is going to change for sure. But that's not the criteria for constant rate of change. The criteria is, do we have a consistent or constant ratio of the changes of those quantities? Okay? So, yes, this doesn't phase us. Because we're looking in analyzing whether or not h and t are in constant rate of change. All of our analysis focuses on changes in h and the change in h and the change in t taken together. Okay, so yes, and what about the last one? Is the change in h a constant multiple of the change in t? So coming over here, is there a number that we always multiply by delta t that will give us delta h? And what is it? Becca says negative 1.2. Again, that constant multiple is the constant rate of change. It's the same as the constant ratio. It's the number you'd multiply by delta t to get the corresponding delta h. So, yes, yes, yes. Now, if any one of these is true, then all of them are true, and you have constant rate of change. We're just practicing all three of them, okay? But if you can show any of those are true, or you know for a fact that any of those are true, that's good enough. And then everything's true. It's got constant rate of change, you have proportionality in the changes, and the other two of those three are true. Okay? Any one of those is false, then the others are false, and you don't have constant rate of change. It's all or nothing. Okay, so what will the graph be in general? Okay, straight line. That's right, so let's do it. Let's show the graph. How many points?
Infinite.
Okay, you guys are catching on? Okay, so infinite number of points, but the ones that are highlighted there as blue diamonds are the ones from our table. Okay, which aspect of constant rate of change would I be illustrating by drawing these segments? Talk with the person next to you. Which aspect of constant rate of change would I be illustrating if I drew those 6 segments? Go. Which one of the 3? Constant ratio, constant multiple, or equal delta t means equal consistent delta h? Go. What's the delta h every time? What is it?
2.
It was these there. Negative 1.8. So this is showing you can't show constant multiple or constant ratio unless you have different numbers, right? So this would just be the identical ratio each time. You're not really showing that the ratio is constant or the multiple is constant. What you are showing here is that for equal changes in t, you always get the same change in h. Now to show the other two, I would need an illustration like this. I could start with no. That's sad. Let's try it again here. All right, pretend the line is there. We won't take the time to do that. But an illustration like this. Now I didn't have to start at the same point each time, but that's one way to do it. Now through that illustration, we could look at each corresponding delta H and delta T, see that the ratios are the same, see that you always have a constant multiple that would give you delta H from the corresponding delta T. So what delta, let's just do the red one, delta H or delta T I'm showing is from, looks like 3.5 to 10. So what's delta T? 6.5. Find delta H, go. What's delta H? Find it. Not by using the H column, but using constant rate of change. Using constant rate of change, how can I calculate delta H? Nick, what would I do to get delta H applying constant rate of change?
Just look at the change.
What's that?
It's just a change in H.
Yep, and I want to calculate it with constant rate of change. What would I do? How about Cecilia? What would we do to get delta H?
Would you use one of the negative
So which one of our three criteria can get this real easily? We know delta T, we want delta H. Nope. Jake?
Delta H is equal to K times delta T.
Right?
And K is negative 1.2.
Right? And?
So you get negative 7.8.
And delta T is 6.5? Negative 7.8. If you have constant rate of change in H is a constant multiple of the change in T. So if we're given change in T of 6.5, the flag is going to go down 1.2 times as much as that. Right? That's what we saw over and over again. So negative 7.8. Constant multiple reasoning. Questions on that? Okay, so open up your workbook to page 35. Does it look like this? Okay, and it says the length of a burning candle decreases at a constant rate of 2.2 inches per hour. The candle has been burning for 3.5 hours and is currently 8.3 inches long, represented by the point 3.5, 8.3 on the graph below. Okay, so we've got two quantities already defined for us. Number of hours the candle has been burning. So that's got all the criteria met for a good variables, and that's our horizontal axis. So we'll stay with convention and say that's our x variable, the number of hours the candle has been burning. And then the length of our candle in inches is a good, well-defined variable. And that'll be our y. Since that's the vertical axis, we'll stay with the convention and make that y. Okay, so they gave us a constant rate of change, decreases at a constant rate of 2.2 inches per hour. So what I want you to do, your task is to represent or make sense of this number, 2.2 inches per hour, in terms of the variables x and y. Who's been paying attention? Make sense of or write 2.2 inches per hour in terms of the variables x and y. Everyone try it by yourself, and then once you think you got it, if you want to have a conversation, can you write that number 2.2 in terms of x and y? Make sense of that in terms of our variables. How about Allah? Did you get it?
Yeah, I think it's a change in y over change in x.
Change in y over change in x equals what?
Well, this is what I'm trying to calculate. I don't have a chance to calculate.
Is there something to calculate?
Well, it should be 2.2.
2.2. You want delta y over delta x to be 2.2. We know that's inches per hour. How did you do? He likes it? Michael, no?
We don't have the delta, we only have one value, so how are we supposed to get the change in it with one value?
Okay. So he doesn't think there's enough information. Tell me your name again.
Andrew?
Andrew, what do you think?
I think sorry, I don't remember.
It's okay, you
the
don't.
first person who spoke, but I believe he's right.
You agree with this?
And that you can use that change in that constant rate of change to find additional points.
Okay.
Using that single.
Okay. So you like this. Other comments? So tell me your name again, I forgot. Yeah.
Freddie?
What is it?
Freddie?
Freddie. What do you think? You agree with this?
Yeah?
Yeah. It's cool with me. Rebecca. She wants negative. Negative or positive? When delta x increases, time goes by, what happens to, or when x increases, the time increases, what does y do? Decreases. Okay. Is it as easy as just saying that this ratio equals negative 2.2?
Yeah.
Can you do that? Why?
Because
Okay, it's because of what we said. We said that if you have constant rate of change, then the ratio of delta y to delta x is constant, and that value is what? The constant rate of change. So that's what they're giving us, the constant rate of change. We just got to include the negative, because when x goes up, y goes down. Right? When x goes up, y goes down. So we're good. All right, so part A says represent a time spent burning of 2 hours, starting from 3.5 hours. So up, down, left, or right? Up, down, left, or right. A time spent burning of 2 hours starting at 3.5. I've heard down, left, and right. Time spent burning, an increase in the time spent burning. So that's going to be horizontal. That's our x quantity. If we want to increase, it's going to go right. You know, sometimes they're straight, sometimes not so straight. That's better. Okay, so that is 2 hours. And how can I use symbols to represent that change? So what equals 2? Delta x. That's right. That red bar, we've seen this before now, represents an increase in time of 2 hours. When 2 hours goes by, the candle is going to increase or decrease in height? Decrease some amount here. Something like this. How can we use constant rate of change to calculate that amount of decrease? That change.
Take the 2 and plug it into the delta y over delta x.
Okay, you could do that. So you want to use this right here.
Yes.
Okay, how can we do it slightly more directly if we want just to know what delta y is? So you're using constant ratio. What could we use and save a step? Look at the other two. What could we use?
Multiply the change in x just by the constant rate of
Yeah.
negative 2.2.
Delta y equals k delta x. What is k? Negative 2.2. Delta x is 2. Therefore, delta y is negative 4.4. So it's almost the same thing as what you said. Just saves one step, right? It saves one step of changing this around. So yeah. So given any change in x, the change in y is a constant multiple if you have constant rate of change, which we do. All right, so now that gives us a new kind of situation. We have now a new point on the graph, which represents 2 hours later and the corresponding length of the candle. So if it's 2 hours later, what is the time? 5.5, right? Okay, now we need the new, we're interested in the new length of the candle. And so we're going to use this principle here. We want the new y. How would we calculate, just in general, the new value of y? Where's that going to come from? What's that? You use minus? I don't think it's minus. Well, so what are you going to start with? Negative 4.4. Okay. Okay, so you're really starting with 8.3, right? You're really starting at the old value of y, and what are you doing? Adding the change, right? This should make sense that if you have a starting value of y and you add the change, you're going to get what your new value of y is. So the old value of y was what? 8.3. How much did y change? Negative 4.4. So we were at 8.3. We changed by negative 4.4. Therefore, 3.9. Okay, so this process hopefully makes sense. Delta x was simply our change in x, delta y. Then we use this constant rate of change, this constant multiple reasoning. That was one of the three things, and said that the change in y would be k times the change in x. And then the new value of y was what you had before, plus the change. And that gave us 3.9. So we have the new corresponding pair, time elapsed since it started burning, and new length of the candle. So I'm going to do the same process again, but this time instead of calling that change 2, so first of all, we had 5.5, 3.7. So as the candle burned, how many points did we get in between? Infinite number, right? And then time can keep going by. We get more points. We could look at earlier for lesser values of time. We'd have more points. And so our goal is, can we write an equation that expresses every single one of those points? Every single one. We're going to use the same process again to do that. But instead of picking a particular point or a particular change in x, we're just going to come along here and say, boom, I can pick any point that I want. I'll pick that one right there. And that's not necessarily 6, so that's unfortunate that I chose it right on 6. So we'll pick it right here. All right, that point right now. We don't know what its x value is because really it's any x value. It's any x value and the corresponding y. And so we're going to, because it represents any x value, we're going to label that point xy. Because I could have picked this one, or 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 this one. It means every and any point on that line. But we're going to do the same process. First step is, starting at 3.5 hours, we want to represent and write the change in x to this arbitrary point xy. So how would I write delta x? How would we calculate delta x? Starting at that point and ending at this arbitrary point xy. What would the change in x be? Tell me your name again. Right here. Sarah, what do you think? So what was our way of calculating the change in value of a quantity? Jacob.
Final value minus initial.
Final minus initial. So do it.
X minus 3.5.
X minus 3.5 calculates that change in x, doesn't it? Doesn't it? Yes. Okay. Now we're going to use constant rate of change to get the corresponding change in y. How can I use constant rate of change to write down what the corresponding change in y is? Michael.
We would be able to do the delta x times the negative 2.2.
Right. K delta x. So do it. So K is?
K would be negative 2.2
Times.
whatever your delta x is.
And what did we find delta x was? Or how do we write it? We just did it. We just wrote what delta x was. What is it?
So
X minus 3.5.
why would you not want to do the delta x symbol in there? So just because it's not calculated yet?
No, because what we're looking for is a relationship of x and y in the end. So we're going to write that delta x in terms of x.
So you're including the actual.
Yep. Okay, then our final step was that new y, which is this one here, equals, what did we say? Old y plus delta y. Should make perfect sense. Should make perfect sense. So y equals, what's our old y? 8.3. And what did we just find for the change in y? Negative 2.2 times. What did we just end up with? So what happens is this x could be any x. This formula then cranks out the corresponding height for the x that you picked. So in essence, it means every single point on the line of the graph. Every single point. And we see exactly where it came from. We started with a change in x. We found the change in y by doing the constant multiple times the change in x. And then we added the old y to the change in y, and it gives us the new y. So you can see it all there. So this is every point on the line. Okay, don't pack up. You're doing one yourself. Every point on the line. The days of y equals mx plus b are over. Okay? If you want to use whatever you've learned in the past to check, to make some comparisons and check, you're welcome to do that. But you're responsible on quizzes, future quizzes and exams to know this process to build the equation of a line, because it uses constant rate of change. And it really focuses you to focus on the quantities, what's happening with quantities together. As time increases, the candle burns, and we can get any corresponding pair of time and length now with that equation. Okay, so quick, flip the page, turn the page, and you're going to find the equation of the line for that graph that you see there, number 3. So you're going to have, there's going to be an initial step that you have to do that's a little bit different than this. Okay, so find the equation of the line. with the same process. You're practicing this process that we just went through. But there will be an initial step you've got to do. Okay, so that we're all on the same page. After you use your basis point, once you start, as the 2.9, 5.16. Use that as your basis point. The 2.9, 5.16. So we all have the same thing. Anybody have the constant rate yet? K equals 2.4? Okay, then you can check what you did against mine. So if you have a question, you can stick around. I'll stick around and answer any questions that you have. You can check.